In this work, we propose a multi-vehicle coordination methodology based on hierarchical quadratic programming. The main idea of this work is to define a hierarchical stack of tasks. The multi-vehicle task function induces specific motion behavior in the group of vehicles. We formulated the task based on two properties, type of function and type of constraint. We refer to global or local tasks, whether it depends on more than one vehicle or just one of them. From the constraint and optimization perspective, a given task could be naturally defined in terms of either equality or inequality. We support our approach with two experiments.
In the first experiment, the group of robots have to perform 4 tasks using a hierarchical approach.
The task with the higher hierarchy is the individual obstacle avoidance. Each robot has to perform obstacle avoidance regarding black fixed boxes and the rest of the robots. The task with the second hierarchy is the workspace region constraint. The red circle is the region to be reached for the robots.
The task with the third hierarchy is the formation distribution.
This task distributes the robot formation with a specific variance in x and y's. Finally, the task with the fourth hierarchy is the group tracking. The group of robots have to track a square time parameterized trajectory. The tracking is performed regarding the center of the formation. Here the experiment. At this point, the robots have reached the circular area. Here, the formation is broken up momentarily because of the obstacle avoidance task has the first level of hierarchy. Robot 4 is able to be in any place inside of the circular area because of the second task was defined as an equality constraint. An external disturbance is induced in the robot 6. Robot 1, 2, and 4 reacts to this disturbance, trying to compensate the desired variance distribution because of the task tree.
The second experiment was focusing on demonstrating the scalability and flexibility of our approach when the tasks are combined with other ones.
The scalability lies in the following concept. Each task induces specific behavior in the robots. We can use different individual tasks and combine them for creating a stack of tasks. Each stack of tasks can be considered as a state. We can create new states, just changing the hierarchy in the stack, or even adding new tasks, and so on. Finally, we can define transition to be able to switch between the states and with that create a state machine. The state machines help us to induce sequential and more complex behavior in the robots. In this experiment, the group of mobile robots have to remove the objects from the work area and place them in a specific location sequentially using a hierarchical task approach. The robots switch between 3 states where each state contains a stack of hierarchical tasks.
In the state 1, the robots have to reach a circular formation around the objects to be relocated, performing individual obstacle avoidance regarding both the rest of the robots and the fixed obstacles.
In the state 2, the group of robots have to move each object to a specific location performing group obstacle avoidance and keeping a circular formation around the object. This avoidance task function is performed regarding the center of the formation.
Object 4 will not be relocated, but it will be considered as a fixed obstacle.
In the state 3, the group of robots go to a home position performing individual obstacle avoidance. Here the experiment. The group obstacle avoidance is performed keeping a circular formation and in a coordinated way. This is caused by the task 2 and 3. Task 4 keeps the avoidance direction always towards the target.
Our approach works even in changing environments.
Each object is considered as an affixed obstacle if it is not being transported. Here, the formation velocity is reduced because of the presence of the dynamic obstacle. If the formation loses the object, they are able to recover it by switching to the state 1. Then, they can continue transporting the object by switching to the state 2. Finally, the robots go to home position by switching to the state 3. For more details about this work and experiments, please refer to our paper.